All right, we're back, Physics 1151, for Wednesday's lecture. We're going to be finishing up the first set of notes dealing with heat engines and refrigerators. Doing more of a superficial coverage here today, yesterday, and today with this set of notes. We'll get into a little more detail about the working mechanisms in the second set of notes, which will be starting in the second half of today's lecture. So where did we end up? We ended up right at refrigerators, air conditioners, and heat pumps, and we'll start there, but I think it's instructive to begin with just a real quick review of heat engines, because we're going to be comparing the heat engine to the refrigeration system. Couple quick notes. Assignment 4, due Friday the 19th at 9 a.m. It's a relatively short assignment. Unit 1 exam, Monday the 22nd, dealing with chapters 15, 18, 19, and only the first 4 sections of chapter 21. Okay. So we ended up with a brief discussion of heat engines, and we saw that a heat engine is a device that uses input heat from some high temperature reservoir to do mechanical work. And so you have heat input and you have work output. Now, second law of thermodynamics says it's impossible to get out as much work as the heat you put in, and that some of the heat inevitably will be exhausted as waste to a cold reservoir. So the second law of thermodynamics says that heat engines, it's impossible by nature to have 100% efficiency. Some of the heat input will always get exhausted as waste, and it's impossible to have the output work be equal or greater to the input heat. And we did the YouTube video with a nice example of a heat engine, and that's the internal combustion engine, which uses the ignition of an air-gas mixture to produce a large amount of heat inside a cylinder, and that is used to turn the crankshaft, which rotates the wheels and which moves your car. And so this is an example of converting chemical energy, the reaction of the gas, to heat, and the conversion of heat to work out. And some of the heat inevitably is wasted, and that is exhausted as waste heat, as exhaust. So that's a heat engine. So it requires a hot reservoir, which is the burning fuel, and it requires a cold reservoir, which is the air or the atmosphere, and then heat flows from hot to cold. Now, this process is consistent with the second law of thermodynamics. Remember, second law of thermodynamics says that heat will flow naturally from hot to cold, and that's our own experience. We'll see in a little bit that there is no way you can spontaneously create a refrigerator. In other words, you can't make heat spontaneously flow from cold to hot. We'll get into that in a minute. We discussed a little bit of the 4 strokes of an internal combustion engine, and we're going to come back to that in the next set of notes. We define the efficiency of a heat engine. Remember, efficiency is always what you get out, which is work, divided by what you put in this case, which is the heat in the high temperature reservoir. And since all heat cannot be converted to work, our efficiency is always going to be less than 1 for any heat engine. So this is a heat engine taking heat from a high temperature reservoir, extracting some of it as mechanical work, exhausting the waste. And you should be able to understand these energy transfer diagrams in the directions of the arrows. Heat enters the gas, used to do work, so you get work out, and you exhaust heat in the cold reservoir. Refrigerators are heat engines in reverse here. So we had the heat, we're going to have the heat engine here to the right, and you have the refrigerator to the left, okay? And this could be, for right now, this could be a refrigerator, an air conditioner, or a heat pump. And the ultimate goal of all of these, the heat engine or the heat pump, or air conditioner, or refrigerator, the ultimate goal of all of these is to extract heat from a cold temperature reservoir and make it even colder, or to keep it cold, and to pump it into a hot reservoir, okay? So there's one problem here. If you look at the heat engine, heat spontaneously flows from hot to cold, so that's no problem. You get work out. With refrigerators, air conditioners, or heat pumps, we're trying to pump heat against the gradient. We're trying to pump it from cold to hot, right? And it's not going to spontaneously go in this direction, according to the second law of thermodynamics. And so this requires heat as an input. Work as an input. We need to put work into the system to pump this heat against the temperature gradient. With refrigerator, this would be a compressor that does this work. And so heat engines, the direction of heat flow is consistent with second law. With refrigerators, air conditioners, or heat pump, we're trying to get heat to flow against the gradient, and so we need to put work in. And so all of these arrows are in the opposite direction. We're trying to pump heat from a cold reservoir to a hot reservoir. So the cold reservoir and the hot reservoir and the means of which work is done vary between these. So here's an example. Let's start with a refrigerator here at the right. The cold reservoir is just the inside of your refrigerator. So we're trying to pump heat out of there, right? We're trying to cool the refrigerator off. So we need to pump heat out of the refrigerator, and the hot reservoir for the refrigerator is your kitchen, or the room the refrigerator's in. Okay, so with this, to pump this heat from the refrigerator to the warm room, we need to supply work. Okay, and this work is done, this electrical energy is the input, and here's your compressor, and that goes into running a compressor, and that does work on the gas to pump it from cold, the inside of the refrigerator, to warm, which is the outside. And consistent with the arrows here, we look at it for refrigerator, work plus the heat extracted must be the heat deposited, QH. Whatever comes into the system, which is work plus the heat extracted, must add up to be the heat removed, or the heat exhausted into the room. And what this says right here is that you're always going to get more heat deposited in the room than the electrical work in to the system. Okay, so you're going to deposit a fair amount of heat into the kitchen. Here's an example of an air conditioner. Right here, the cold reservoir is the cool room, and we want to keep it cool. So we need to pump it into a warm environment, which is the outside, the warm outside, and you get a compressor in here again, which using electrical energy is used to pump heat from cool to hot. And heat pumps behave the opposite. Here, with a heat pump, you're taking heat from the cold outdoors and we're bringing it into the warm room and depositing it. And so all three of these, a heat pump, a refrigerator, and an air conditioner, are used to bring heat and cool an already cooler room by depositing heat into a warmer environment. So you've taken a physics class and you go home and you want to show off your newfound knowledge, and so you have this very clever idea on a warm summer day to cool your kitchen by leaving the refrigerator door open, or to cool your room by putting an air conditioner on the floor by the bed. Okay, will this work? Okay, take a minute. So in other words, can I use a refrigerator, leaving it open, the door open, and can I use it to cool the room? Okay. Now, the answer is no. And I hope, please don't go home and do this. And if you do, like, please don't claim I was your teacher. So why can't we do this? Okay, well, you will only if you look at right here, here's QC is the amount of heat you extract from the cold reservoir, and this is going to do work, and you're going to exhaust even more heat than you extracted into the warm room. So if you leave the door open inside your refrigerator, you will remove a little bit of heat from the inside of the refrigerator, but you'll exhaust even more of it out into the room. And so the net effect is that you will warm the room. The room will warm the temperature will rise even more than if you did not do this harebrained idea. So don't leave refrigerator doors open in the summer to cool your kitchen. Okay, it's just a bad idea. Okay, so it violates the second law of thermodynamics. So the answer is no. Okay. Now, we need to define, just like, where am I here? The performance, whereas a heat pump, we define the efficiency of a heat engine as what you get out, which is the output work divided by what you put in, which is the input heat. With a refrigerator, we define a similar figure of merit, which is used to compare refrigerators, called the coefficient of performance. Okay, it can either be called CP, coefficient of performance. Your author uses K. Okay, and what we get out here, it's the output, which is QC, how much heat we're able to remove from the cold reservoir, divided by what we put in, the input mechanical work into the system. Okay, so it's what we get out, QC, divided by what we put in, WN. Okay, and unlike efficiencies, these coefficients of performance can be greater than 1 and often are. We'll see in a little bit. So the bigger the number, the better. The more heat we can extract, QC, for a given amount of work in. So when comparing, a bigger coefficient is better. Now, the second law of thermodynamics says that we can't have a perfect refrigerator. In other words, Wn cannot be 0. We have to put some work in to move heat from cold to hot. And so a coefficient performance of infinity is impossible by the second law of thermodynamics. So this is our equation for assessing the efficiency of a refrigerator. Heat pumps, it's slightly different. Where is it? Because with a heat pump, you're pumping air from a cold exterior into a warm interior, right? We're pulling air out from the cold, and we're trying to warm our house with it, right? And so here the output is QH, how much heat we're able to pull into the warm house, transfer in, divided by WN. And so this coefficient of performance, the equation is slightly different for a heat pump than it is for a refrigerator, because here we have QH instead of QC in the numerator. So you have two types of heaters here, and both of them are sometimes used to heat homes. The first is you have an electric heater, okay, like a baseboard heater in your house, and this uses a heating coil. And the second is you have a heat pump. And so the question is, by and large, which is a more efficient way of heating the house? Baseboard heating, using a heating coil, or a heat pump, which uses work to extract heat from a cold environment and pump it into your house, a warm environment. So the answer is that a heat pump will always be, for a given amount of electrical work and a given amount WN, a heat pump will always give you more QH, a greater QH. And so one way to see this is that if you have a coil here, and I put 100,000 joules of electrical energy in, the heating coil will basically, all of this electrical energy will be converted into heat. Okay, so QH is 1,000, the work in is 1,000, and so if we look at our efficiency, QH is 1,000, WN is 1,000, the coefficient of performance will be 1. Okay? In other words, all of the electrical energy is converted into heat. Okay? Now with a heat pump, we see that the heat extracted from the cold outside, QC, plus the work add up to be QH. Okay? And so this sum is greater than W. Remember, for the heat, for the electrical heater, W, the work in, is equal to QH. Here we have a bigger number than QH. Okay, so the coefficient of performance for a heat pump will always be larger than for a baseboard electric heating system. So in other words, for a given amount of work, you will always get a greater QH with a heat pump than you will with the baseboard heating. Now, that being said, as it gets colder and colder outside, this efficiency, the amount of heat pulled in, QC, gets smaller, and so this number can get close to 1 on very cold days, and so the efficiencies of heat pumps tend to decrease when the weather gets very cold. They don't work quite as well because there just isn't, pardon my jargon here, there isn't as much heat to pull in from the cold, and so your coefficient of performance decreases. As I found out with my $220 electric bill last month, wasn't good. So heat pumps tend to work better than the baseboard electric heating, but their performance when it gets really cold outside decreases some because they just aren't able to pull in as much heat from the outside and deposit it into the inside. So typical values 3 to 4, sometimes up to 5, but this is greater than 1, which it is for electric baseboard heating. And so basically, beating this to death a little more, another statement of the second law of thermodynamics as applied to refrigerators, it just says there's no perfect refrigerator. You cannot spontaneously get heat to flow from cold to hot. We always have to put work into it, which means that the output QH has to be greater than the work in. Okay, in other words, we are always going to deposit more heat into the warm reservoir than we extract from the cold reservoir because you have to do some work on the system too. So let's finish with an example here. So each of these energy transfer diagrams represents a hypothetical heat engine or a hypothetical heat pump. Okay, and these numbers here are the corresponding heats and work. Okay, only one of these hypothetical situations is allowed in nature. Which is it? So pause your video here, look at each one of these, and determine which one of these 5 is allowed in nature and why the other 4 are not. Okay. All right, we're back here. So let's look at the first one, heat engine 1 here. And that's a heat engine, right, because heat is flowing from hot to cold and we get work out. So here comes heat flowing from a hot reservoir, and if you look at the directions of the arrows, heat in, work out, heat extracted, this is a heat engine. So why is this not allowed in nature? Okay, well, second law of thermodynamics says you can't get more work out than the heat you put in, right? Here the work out is 400 joules, heat in is 300 joules. Not allowed. Okay, so process A, this heat engine A is not allowed in nature. Okay, why does this not work? So what is this system right here? Okay, here you have heat flowing from cold to hot, so it's supposed to be some sort of refrigeration system, right? Only problem is you've got work going out, and the second law of thermodynamics says that that means heat will spontaneously flow from cold to hot, which we know does not happen, right? This W arrow needs to be flipped. You need input work in order to exhaust heat from cold to hot. So this is not, B is not allowed either. Okay, so let's look at C. Okay, again, this is a refrigerator. If you look at the directions of the arrows, we're taking heat from a cold reservoir and we're trying to pump it to a hot reservoir. So it's a refrigerator. Okay, good. Work is going input into the system. Good, we need work. Let's add these up, okay? 100 joules of heat of work is needed to extract 400 joules of heat from the cold reservoir and exhaust 500 joules, which is the sum of the work plus QC, into the warm reservoir. So this one's okay, all right? So C is allowed by nature. This is a refrigerator. Let's just, for kicks, look at D and E, and we know the answer. There's only one allowed. So let's see why D is not allowed. Okay. Well, again, here you look, okay? What this says is that we know from the second law of thermodynamics that you're going to exhaust more heat, QH, than you're going to pull out, QC, right? So here we're pulling out 400 joules of heat from the cold reservoir. We're doing 100 joules of work, and we're only exhausting 300 into the hot reservoir. Okay, that's not allowed. Okay, so D is not allowed. Then E is pretty easy, right? E says that all 400 joules of heat from the high temperature reservoir are used to do work. None of it is exhausted to the cold reservoir, okay? And there is no perfect heat engines. This implies an efficiency of 100%, which we know doesn't happen in nature. So process E is not, the heat engine E is not allowed. So you should be able to, on an exam, interpret these heat transfer diagrams, and you should be able to understand the processes and why a given engine is or isn't allowed. You should be able to calculate the efficiency for heat engines, or the coefficient of performance for a heat pump or for a refrigerator. And you should be able to explain why some of these are allowed and some of these aren't. So now we're going to move on to the second set of notes with Chapter 21. Okay, we're going to start the second and final set of notes for Chapter 21. What we're going to do, so in the first set of notes, we introduced the heat engine and we introduced the refrigerator. We looked at the energy transfer diagrams. With the heat engine, we looked at the YouTube video. We're going to go through that a little bit more detail now. So we're going to cover heat engines and refrigerators in a little bit more detail. We're going to look at the PV diagrams and study the individual segments in the context of the first law of thermodynamics. So it never hurts to do a little bit of review, so we're going to start off by just a real quick review of heat, work, and energy. Then we're going to look at the PV diagrams of heat cycle engines in general, and then we're going to discuss the practical example of the internal combustion engine for your vehicle, cover refrigeration cycles, and the model of the refrigerator. I think we're probably going to end up with item 3 here, the heat engine, and then get into refrigerators tomorrow, which will finish the chapter. Just a reminder again about your homework, due Friday the 19th, your exam on the 22nd, and again, on chapter 21, we will only be going up through section 21.4. Okay. So here are the the objectives for this unit. These are what you should be able to do on the exam. So take a look at these. Again, let's just, if you know all this and it's easy for you, skip ahead in the video, but I don't think review ever hurts anybody. So the first law of thermodynamics, remember, said that the heat added to a system is equal to the work done by the system plus the change in its thermal energy. And that's basically, for gases, it's temperature amounts that changes in temperature for the most part. And remember that the work done by the system, we're doing these PV curves, these pressure volume curves, quite a bit in the course here. And the work done in going from state 1 to state 2 is just this area under the PV curve, right? And that depends on the process. And so the sign convention can be a little confusing, but the easiest way for me to remember is that the external work is positive for a compression, right? Because the external force, is in the same direction of displacement. It's compressing the fluid, okay? And the external work is negative for an expanding gas, an expansion, because the gas displacement is going outward, and that's against the external force, so that's negative. And then remember the work done by the system, which is typically what we use more in practical thermodynamics than the external, is just the negative of this. So the system work, again, is just the area under the PV curve, and the system work is positive for an expansion, right? The pressure is pushing outward and expanding the gas, and the system work is negative for a compression. So you should be able to, on an exam, calculate work. And we saw that for closed processes, that the work done by the system is just the area enclosed by this closed cycle here is WS. So that's work. You should be able to use that along with the ideal gas law, right? PV is nRT. Depending on which is constant, meaning the given type of process, you should be able to apply the ideal gas law to relate the initial state variables to the final. And so combining the ideal gas law with the first law of thermodynamics, you should be able to do this. And then remember, for the engine or refrigerator, the process is cyclical, meaning it ends up at the same temperature, pressure, and volume as it started, and so the change in the thermal energy is zero. And for these cyclical processes, these engines and refrigerators, delta E thermal is zero, and you just get that Q is equal to WS. Now remember, there's this WS, the work of the system, that's the mechanical work, and so for a heat engine, this is the work out. WS is work out, and for a refrigerator, WS is the input work, W in. So these are important equations. You need to be able to, on the exam, understand these processes, these four processes. Isochoric, what does that mean? That means constant volume. Delta V is zero, okay? Delta V is zero means no work is done, okay? So the first law says that the heat added is equal to the change in the thermal energy. Isobaric, what does that mean? That means constant pressure. Pull P out of the integral, and the work is P times delta V. Isothermal, constant temperature. we derived that in the last chapter, right? For P, you put in P is equal to nRT over V. You put that in the integral. You integrate that, and you get this equation for the work for isothermal. So for for adiabatic, Q is 0. So you should be able to, for each of these processes, you need to understand what's going on for each of the 4 types of processes. What are the implications for the ideal gas law? Adiabatic's a little more complicated as far as relating initial state variables and final. You should be able to calculate work definitely for isochoric, isobaric, and isothermal. Adiabatic's a little more difficult. Heat added is just from the equations for the heat capacities at constant pressure and constant temperature. And you should be able to write the first law of thermodynamics for each of these 4 processes. So this table is very important for the exam. I also found a nice little summary from the end of the chapter in your text, which summarizes a lot of the important information from the last chapter. So you should go back and look at this stuff. But you have to understand these 4 processes. You have to understand work, how to calculate it. For the closed cycle, it's just the area enclosed. So this is some of the most important information in the unit. So I encourage you to take a look at these slides. So let's start with a concrete example here. So here we have an example of a heat engine, a hypothetical heat engine, and it's a closed process. And the cycle is consists of 3 processes. Process A, which is adiabatic, meaning no heat is added. Okay? Process B is isothermal, meaning it's carried out at the temperature's constant throughout this process. And constant C, process C, is again an adiabatic process. So A and C are both adiabatic. Author didn't do a very good job of putting an arrow at C, but that's also adiabatic. Okay. So what we want to do here is we're going to make a table for each of the processes. Okay, A, B, and C, and for each of them, if the change in the thermal energy increases during that process, we're going to put a plus. If it decreases, we'll put a minus. And if it stays constant, we'll put a 0 if it doesn't change. And we'll do the same for the work done by the system and the heat added to the system. We're not worried about calculating numbers here. We're just putting in plus, 0, or minus to indicate what if it's changing in positive direction, negative, or not changing. And we also want to understand each process. So for each of these, we're going to summarize, in words, what is going on here. And there's a homework problem like this. And there's also another one where you're going to do this for a real gas engine, the Otto cycle, and you're also going to do this for the refrigeration cycle. So important to understand this example here. So let's look at process A here. A is an adiabatic process. Okay, what does that mean? Well, it means, let's look at what's happened. We start at a high pressure and a low volume, and we're going to a low pressure and a high volume. So in other words, the gas is expanding adiabatically. Okay? And what is going on here is no heat is added or removed from the system. And that either could be because it's well insulated, or for a car engine, the intake and exhaust valves are closed, or it could mean that the process is so fast that no heat can enter or leave the system. Okay, so let's just look at this first process, A to B. So Q is 0, and so the first law of thermodynamics says Q, which is 0, must be equal to the work done by the system plus the change in the thermal energy. Okay, and the thermal energy, remember, is basically it's measure of a change in temperature. So for process A, we put Q as 0. No heat is added or removed. Okay. Well, that means that the change in internal energy, the change in the thermal energy, must be the opposite sign in equal magnitude is the work done by the system. Okay. Now, to determine the sign of the work done by the system, it's easy, right? The volume is getting larger. The gas is expanding. And so that means that positive work is done by the system in expanding the gas. So that means W plus is 0. W plus is the negative of delta E thermal, which means that the thermal energy is decreasing. Okay. So what's this saying in words? It says that when a gas expands without heat being added, meaning adiabatic, it cools. So the gas does work in expanding, and that work cools the gas. Okay, the change, it comes at the expense of thermal energy. So work done by the gas when it expands adiabatically results in cooling. And so this is important. Okay, this is important for any gas. If a gas expands and heat is not added and work is done by the gas will cool. Okay. So that's process A. Process B here is isochoric. Well, why is it isochoric? Well, the volume isn't changing as we're going up here. The volume is constant. So here the volume is constant, and since the volume is unchanged, remember, work is equal to the integral of pressure times the change in volume, and so if dV is 0, there's no work done. The gas doesn't do any work. So Ws is 0 here, and the first law says that Q is equal to delta E thermal. They're the same sign, and they're the same magnitude. Okay, so what this says here is the pressure is getting larger because heat is being added to the gas. So if the gas can't expand, meaning the volume is constrained, all of the heat goes into raising the temperature of the gas. And since PV is nRT for an ideal gas, if V is constant and pressure increases, the temperature must increase. Okay, so basically what this has done is increasing the pressure and the temperature of the gas at constant volume. Okay, so in other words, if heat is added to any gas at constant volume, all of the heat will go into raising the gas's temperature and pressure. So that's step 2. And so for this process, we write Ws as 0 because there's no work done. And we write that Q and delta E thermal are both positive. Okay, so that's step B. Now we have another adiabatic process in closing the loop here. Only here it's an adiabatic compression. We're starting at a high volume, and the gas is being compressed adiabatically to a lower volume. So right away, adiabatic, what does that say? Q is 0. No heat is being added or removed. Okay. So Q is 0. Or sorry, this is isothermal. I screwed up. Sorry, this is an isothermal process. So change in temperature is 0, and therefore the change in the thermal energy is 0. Okay, so delta E thermal is 0. My bad. Okay, delta E thermal is 0. If a gas is compressed isothermally, meaning at constant temperature, then the first law says that the heat added to the system goes into doing work. And so heat is added, and that goes into compressing the gas. We end up at a higher pressure, lower volume, same temperature. So all of the heat goes into compressing the gas. Okay, so it goes into work. And so work done in the gas when it's compressed adiabatically. Yeah, all right. Sorry, not thinking very well. And so you should be able to do these diagrams and explain what's going on for these for the heat engine and for the refrigerator. Here's another example of how to combine work heat in these PV diagrams. Is what is the thermal efficiency of this heat engine? So here we're given its pressure volume diagram, and again it's a closed loop. So remember, what is the work? The work is equal to the area enclosed by the PV diagram in this certain cycle. And the efficiency, the thermal efficiency, is equal to the work output, which is this area enclosed, divided by QH. Okay, and so we want to know, what we need to calculate is first, what is the work? And then we need to divide by QH to get the efficiency. So let's do that. So remember, work is just equal to, for a closed cycle, like a heat engine or a refrigerator, the work output for a heat engine or the work input for a refrigerator is just the area enclosed by the loop here. And so this is a triangle, and so it's 1/2 times the base times the height. And so the base is 0.1 meter cubed is the change in the volume. And the height is 20,000 pascals, or 2 times 10 to the 4 pascals. And so 1/2 of base times height is 1,000 joules. So 1,000 joules of work is the output of this heat engine. Okay. So QH, the heat in, is 4,000 joules, and so 4,000 joules in, 1,000 joules of work out. The heat engine is 25% efficient, and so the answer is C. So on a quiz or a test, I could also ask you, instead of the efficiency, I could say, well, what is QC? How much heat is exhausted into the cold reservoir? Okay, well, if 4,000 joules comes in of heat, and I get 1,000 joules of work, then 3,000 joules must be extracted, exhausted as heat to the cold reservoir, and so QC would be 3,000. So on the exam, you should be able to do calculations like this. You should be able to calculate work for simple geometries here, for simple processes, and you should be able to relate that to QH and to QC. So I think we're going to stop here, and we will start tomorrow's lecture with the practical example of the heat engine, and then we'll go on to the refrigerator tomorrow. So we'll stop today. Tomorrow we'll finish off this set of notes, and that will conclude our discussion of Chapter 21 and Unit 1. Have a great day.